Good morning. Today we will discuss about the different characteristic parameters of process plant. In our last class, we have discussion regarding basic fundamental aspects of process control and control actions. Now, the process plant, as we have mentioned in last class also, that process plant itself is a complicated part of the control loop. So, for designing a particular control loop, different characteristic parameters are to be analyzed. All these are characteristic parameters of process plant. So, the characteristic parameters are self-regulation, potential value, process reaction rate, process resistance, and process capacitance, and process time lag. All these are important process parameters for process plant. These are the parameters for process plant. Now, self-regulation, all the names describe their features. Self-regulation is the property. Self-regulation, self means by its own action. This is the property of a process plant by which the process attains a steady state by its own action, whenever any disturbance is produced in the process. This is the inherent feature of process plant. If the process variable deviates from the steady state due to certain disturbance, then after a certain time delay, it can attain a new steady state by its own action. Say, this is the level filling tank system, where this is the inlet flow rate, inflow rate, and this is the outflow rate. Outflow is the controlled flow, inflow is uncontrolled flow. So when the inflow and outflow is equal, then it will attain a steady state level. So suppose C is maintained a steady state value whenever the inflow and outflow is same. Now, if due to certain disturbance in the inflow, it may be due to the restriction of this inflow path, maybe the flow rate increase, whatever, there are several load variables may cause the change of inflow. Then what will happen? If suppose if inflow rate increases, then what will happen? Suddenly the level will try to increase because the outlet flow rate remains in the previous flow rate value. So there is a inequality between the inflow and outflow. So the outflow, as a result, the outlet will, the level will maintain some rise of level, and after a certain time delay, what will happen? As the level increases, the pressure of the column will rise. Accordingly, it will cause the rise in outflow rate. It will measure the flow rate, and accordingly the control action will be taken, whatever be. So after a certain time delay, again the inflow and outflow rate will be maintained a certain relationship, equal relationship, so that a new steady state will be maintained. Instead of maintaining the previous steady state value, a new steady state with certain increase in level will be maintained, and that is by its own action. Due to rise in level, the outflow rate will also change, and due to the this is the inherent property of the process plant. This is called self-regulation. Next is potential value. Potential value is the is defined as the process variable value of the process variable maintained at the steady state condition due to the effect of self-regulation of the process. So, what I am telling, that process variable, this is the process variable maintaining a steady state condition due to the effect of self-regulation of the process. Say for this example, for a level of the tank is the potential value, because this is maintained at certain steady state value for inflow outflow rate equality equation, and whenever there is a change due to certain load variable change or due to certain inflow rate change, then it will again maintain a new steady state value, maybe increased, maybe decreased, whatever be, but a new steady state value of the level will be maintained due to self-regulation. So that is the potential value. Next is process reaction rate. Process reaction rate is defined as the maximum rate of change of control variable following a state change of the final control element in a control loop. Be clear about the process reaction rate. This is the maximum rate of change of control variable following a state change of the final control element in a control loop. Say for this example, the process value changes due to the state change of the final control element. Say the final control element is maintaining a certain value, so that the opening of the valve is at some position. So a certain flow rate is maintained through this path. Now, if due to sudden change the valve position changes, then what will happen? If the path increases, that means if the gap increases, opening increases, then the flow rate will increase, or if the path gets restricted, then the flow rate will decrease. So depending on change of the final control change of the state final state of the final control element, that means whenever set value changes, then level will accordingly change. So process reaction rate is the maximum rate of change of process variable or control variable. Say for this, the level will change from the initial set value to the final set value, and the reaction curve, this is called the process reaction curve, that will follow this type of path. This is the initial position of the final control element due to previous set value, and this is the final position of control valve due to change in set point. So level will follow these characteristics. This is called the process reaction curve, and from the slope of this curve, the process reaction rate can be calculated. Next is process resistance and process capacitance. Process resistance is whenever it is restricted. This is the obstruction to the flow of the process quantity by a process device or element. This is analogous to electrical resistance. This is uncontrolled flow, but this is the restricted path. So there is a obstruction in the flow path. This is analogous to electrical resistance. So whenever there is a restrictor in the flow path, that is equivalent to electrical resistance and called process resistance. Actually, in order to model the processes in terms of process resistance and capacitance, like electrical models, equivalent models, we will use these analogies. This is process resistance and process capacitance. Again, this is analogous to electrical equivalent. That is, the process capacitance of a storage tank is defined as the process quantity stored in the process to the potential value, just like electrical system. C is the stored charge. This is the quantity of process value, process quantity stored in the process, and the voltage in electrical equivalence is equivalent to potential value in this case. So potential value here is this small c. Do not confuse, this is the electrical equivalence of capacitor. This is process capacitance, capital C, and this small c stands for the potential value. This is this V, equivalent to V. Now, C dV dt is equals to dq dt, that is the rate of flow of process fluid, like rate of flow of current. For this case, this is rate of flow of fluid. Say, for this example, this is a storage tank where there is a inflow, uncontrolled inflow, and no outflow path is shown here. So if the inflow is there, then the level will rise, and after a certain time it will overflow. Say, if for a certain flow rate m, if the level is C, that is the potential value is C, that is C dV dt. So C stands for process capacitance. This should be dC dt equals to m. M is the flow rate. This is analogous to current, electrical current. So using Laplace transform, C is equals to m. So the potential value C can be related with the flow rate m as 1 by Cs. So the transfer function is 1 by Cs. Now for this system where there is an inflow and outflow path, the again the level is at certain point is C. Inflow must be m, like the previous one. So m and the outflow is q. This symbol stands for without restrictor, uncontrolled flow. So this m and this is q. So for steady state, this C, the C dC dt must be equals to this m minus q. So again, from here we can say this level C, that is the potential value C, is equals to 1 by Cs. One thing, this capital C and small c, this is a mistake. This should be capital C, 1 by Cs, and this is also 1 by Cs m. So this is capacitance, process capacitance, and this C stands for level or potential value. Do not confuse. Both are small c, written over here. This is also, but this should be capital C, should be corrected. Okay. So this C is represented, that means the relationship between the level and inflow outflow m and q will be like this. This is the model of this process plant. Now for this example, where inflow is m and the outflow is the restricted flow. Then again for steady state this C, the electrical equivalence is C dV dt, that is C dC dt equals to m minus q. Now this q, the outflow rate, should be written as this column level, that is C by the restrictor R. So like I is equals to V by R. So the rate of flow Q is equals to the level C by the restrictor value process resistance R. So by Laplace transform, and we can refer the model as this C, that is the potential value C is related to the flow rate M by this relationship, and this is R by C. This is RC, and this RC stands for tau, that is the time constant. This is just like the first order model, like CR network. For a RC network, the model looks like exactly similar to that. So this potential value is now related with this, and this tau is time constant. So this tau is due to the process time. This is the time constant, or called the transfer time lag. This is due to the time of energy transfer due to this process resistance and process capacitance. I am coming to the detail of transfer time lag and process time lags, but before that, this is an example given for a system tank, where the outflow from the tank is equal to this and inflow is M. Since I have shown 3 examples for tank modeling, you can model this and find the transfer function for this kind of fluid flow system. This is you may consider this as assignment. Next is process time lag. Process time lag is the difference between the time, this is the differential time between the instant of occurrence of a disturbance in a process and the instant at which the corrective action is produced. See, this is the process variable, and x-axis corresponds to time scale. This is the point of occurrence of disturbance, and this is the point of corrective actions. There are some other processes also, some other delays also, but this is the total time delay, where the point error or deviation occurs and where it is corrected, and between these there is a time delay where it is detected. At the point of occurrence of disturbance, the error is not detected. So the total time delay is the differential time between the point of occurrence of deviation to the point of corrective action where it is taken. And there is a 2 stages of time process time delay or process time lag. First is distance velocity time lag or dead time, and the next part is transfer time lag. Distance velocity time lag or dead time is the time taken by the process fluid to travel the distance between point of occurrence of a disturbance and the point where it is detected. This diagram is typically for distance velocity time lag. not for the overall process time lag. Overall process time lag is the differential time between the point of occurrence of disturbance and point of correction, where the corrective action is taken. That is the total process time lag. And distance velocity lag is the time taken by the process fluid to travel the distance between the point of occurrence of a disturbance and the point where it is detected. Then that distance travel is if it is L, then this L is d by v. D is the distance traversed and v is the fluid flow rate, fluid velocity v. So this is for say step type input, this is for ramp input. So this L is the time parameter, unit is time unit, second. This is the distance velocity time lag. So there is a two-stage time lag. One is the point of occurrence of disturbance to the point of point where it is detected. That is distance velocity lag or dead time. And next is transfer time lag. So next is transfer time lag. Transfer time lag is the time lag produced in a system due to delay in transferring energy from source to the process through process resistance and process capacitance. What I am telling, that transfer time lag is the time lag that is produced in a system due to transferring delay, due to transfer of energy from source to the process through process resistance and process capacitance. That is the transfer time lag. So there is two-stage time lag. First is dead time lag, that is the point of occurrence of a disturbance and where it is detected. And second part is transfer time lag, that is due to transferring of energy from source to the process through process resistance and capacitance. I am explaining this process resistance capacitance, through process resistance capacitance, the transferring of energy with the heat exchanger example. And say this is the characteristics for process time lag. Say this is input and the steady state is detected here. This is again time scale. So the observed output is this much. So this is the time constant as we find in RC equivalent model for a tank system where restricted outflow and inflow, uncontrolled inflow was there. So for that we find that the first order model and the time constant tau is derived there. That is the process where the energy transfer through the process resistance and process capacitance, and that time lag is called process transfer time lag. And as per British standard specification, the transfer time lag is defined as the time lag produced between the output characteristic and input characteristic at the steady state when the input signal is a ramp input. This is the standard definition for as per BS specification given in volume number this and section 2. This is the transfer time lag example. Okay, I will explain the transfer time lag example with heat exchanger, as we are familiar with the heat exchanger example already. But this is an example given here that a pressure vessel, this is the pressure vessel having capacitance C and being pressurized from zero initial pressure through a valve of process resistance R. See, the pressure vessel which is to be pressurized from zero initial pressure, the process capacitance or the vessel capacitance is given as C and the restrictor through the process resistance of R. So find the expression for dynamic characteristics of the system. When the pressure vessel is being pressurized, two cases are to be considered. When the pressure vessel is being pressurized from a constant pressure source and when it is being pressurized from constant speed pump. So whatever be the type of pressurizing method, that is through constant pressure vessel or constant speed pump, the pressure vessel is a container which is to be pressurized from zero initial pressure having capacitance C and through the restrictor R, that is common for both. So the electrical equivalent model, this is the pressure vessel which is to be pressurized, that is P2, and the source P1. This is general, not the constant speed pump or constant pressure pump, whatever be. This is the P1 and through the restrictor R and the pressure vessel capacitance C. So in general, this is the equivalent model. So the flow rate Q, that is equivalent to current, is the pressure difference P1 and P2 through the restrictor R. So P1 minus P2 by R is the current flow, that is equivalent to fluid flow rate Q. So if we find this, that is P1 minus P2 by R is equals to Q, and that is 1 by C, P1 minus P2 by R, that is differential, that is dP2 dt, and this is P1 minus P2 by RC, that is tau. So taking Laplace transform, this P2 is modeled as 1 by tau s plus 1 P1s. This is just like RC first order model, right? RC first order model. So this is the generalized relationship between the pressure vessel which is to be pressurized and from through which it should be pressurized. Now for the first case where it is being pressurized from constant pressure vessel, that is P1 is a constant pressure vessel, so this is PC. So this P1S is PC by S. Now putting this to this expression, we can get that this P2t in time frame, P2t is PC 1 minus e to the power minus t by tau, and we are very much familiar with this type of expression. So, and you can understand the response characteristics for this P2 with time. And for the second case, this is the equation of dynamic characteristics of the process. So at steady state, P2t is equals to the constant value, and at P2t is at tau value, that is at 63.2% of PC. At t equals to tau, the P2 value is equals to 63.2% of PC, just like the first order RC model with a constant pressure source. Now for constant speed pump, for constant pressure pump, it was a PC, a constant pressure value. For constant speed pump, this should be a time variable, so K into T. K is the rate of increase of pressure at the outlet of the pump. So P1S is K by S square by using Laplace transform. So just put it here and find the corresponding time value in time plane P2T in terms of P1T. Now this is the example of different time lags for typical heat exchanger. This includes all the process time lags for a closed loop control system with an example of heat exchanger. This is the process plant, that is the heat exchanger unit, where the for heat exchanger unit there must be two inputs, that is one is cooling media, maybe oil feed, maybe water feed, whatever be. There must be a cooling media as well as the heating media fluid flow. It may be steam or other type of or hot fluid flow. And within the process plant or within the device, it will exchange the temperature between the cooling media, cooling fluid and heating media. And the outlet of the process plant should be maintained at certain desired temperature. This is the typical purpose of heat exchanger unit. So the outlet temperature should be maintained at the desired value. So within the device, that mechanism will happen, that is the cooling media and the heating fluid will exchange the temperature, exchange the heat, and so the outlet temperature can be maintained at certain desired value by measuring and controlling the process. So the outlet temperature, which is to be detected by the detector or measuring system, and then the measuring system and the signal should be transmitted to the controller through transmitter. Then controller will compare the measured value with the set value, this is the set point input, with the set value, and accordingly it will generate the control action signal so that the valve will open or close accordingly in order to adjust the energy flow. So there must be a cold media fluid flow, must be cold media fluid flow, maybe water, cold water or other feed material, and the this is the heating media fluid flow, maybe steam or hot fluid. So within this there is a supply side capacitor and demand side capacitor. Demand side capacitor, that is for cooling media, there is a demand side capacitor, and for heating media there is also another capacitance for supply side. And the transfer resistance, that is due to the restrictor. Say the cooling media flows through some pipe, not that the within this the both fluid mixes, and not that. Say the cooling media flows through a jacketed pipe, and through the wall heat exchange occurs, and the outlet is obtained from the demand side. So there is a RC relationship between this transfer resistance of the pipe wall resistance and the capacitance, demand side capacitance, and there is another RC relationship between the supply side capacitor and the transfer resistance of the pipe. So this causes the transfer time lag, and all these are several time lags, that is due to detection there is a finite time delay, then by measuring system and due to signal transmission there is a delay, then controller will compare the signal with the measured value, with the set value, and accordingly it will generate the corrective action, and it goes to the final control element again through some signal transmission system. So there is a time delay. Then the energy flow rate is adjusted to the process, so there is a time delay. And finally, within the process plant there is a time delay that is due to process, transfer time lag, that is due to this capacitor and transfer resistance of the pipe. So these are the several time lags in a typical process control unit, and this is for the feedback control system. In last class also I have mentioned that feedback control system, mostly feedback control systems are used in process plant, mostly because of easiness of connection and application. But the major disadvantage of this, there are several time lags in the process. And another issue is the error is unavoidable. Unless deviation or error occurs in a process, no corrective action can be taken. So once the process value deviates from the set value, then only the controller will run and accordingly the signal changes. So error is unavoidable for feedback control system, but that is the correction level for using feed forward control system. We will explain in next class the feedback and feed forward control schemes. So thank you for today's class.